So are you able to see the board? Hello?
Yes, sir.
Okay, okay, fine. And also I uh, clicked on this sharing with through this YouTube. I don't know if it is publicly, I mean, if it is viewable, but in any case, I think the link I can share with you all through Moodle, and that should work. So let us start. I wanted to say, make one announcement. From this week onwards, there will be tutorial for this course. There are three TAs, and we will divide the whole class into three groups. Each group will have 20 students roughly, and yeah. So I just tell you the names of these TAs. TA for this course. Tejas. They are all second year students. Tejas, okay, and Vishnu, Kadri, and Naman Kumar. Okay. So further information about this tutorial, our scheduling, and so on, you will receive from the TS. Okay. So I strongly suggest that you stick to your group throughout the course. But if you miss for some unavoidable reason attending one of the tutorial classes, you may attend a different one. But keep this to a minimum. Okay. The main reason being that each person may do it in a slightly different way. But if you stick to one person, the entire portion will be covered. Otherwise, some topic may be left out. And if you have any doubts regarding the course content, you can email them or send them a WhatsApp message. They will be able to share with you the relevant information and media through which you can ask your questions. And so that, I mean, before, well ahead of the thing, and so they can think about it and come to the tutorial hour and they can clear your doubts. Same way, if you have difficulty with any specific problem or something. Okay. So, yeah, be in touch with your TAs. Don't ignore this. This is a additional resource that you can make proper utilization of it. Um, uh, First of all, I'm operating from my home, not from my office, so we don't have office hours. So this is a good chance for you to get your doubts cleared outside the class. Okay. All right. So today, let me start with some problems. Yeah. So last time I talked about this. I think towards the end of the lecture, Bertrand's paradox. There was some discussion. Yeah. Um, so the uh, main takeaway from Bertrand's paradox is that your answer very much depends on the probability measure. That's a technical answer. A more pedestrian answer would be to say that the model that you use for your problem uh, will uh, influence the final answer for your question. So there is somebody once said that all models are wrong, but some models are very useful. So okay, let us move on. By the way, this type of problems are called geometric probability. Okay, so is a name. Let's go on. Today I want to start with this another problem, very famous problem. But this is not leading to a paradox. You can make specific calculation. So this is called I don't know how to pronounce his name. He's a Frenchman, I suppose. Maybe it's pronounced as Buffon. I don't know. Buffon noodle problem. A needle problem. Oh, needle problem. So I explained the problem for you. So the thing is, you imagine a plane which is, you know, like this page. So ruled by parallel family of parallel lines, and the space between any two parallel lines, let us say, is so is a 2a. Okay, so a plane is ruled by parallel lines which are hmm, at uniform distance, at a uniform. So any two successive ones which are at a uniform distance. Well, I don't know what to say. Okay. Which are at successive ones, such that the successive ones lines are at a distance 2a, okay, from each other, and a needle of length 2L. So this 2A, 2L is for some convenience, where L is, let us say L is less than A, strictly less than A. So length of the needle is less than the the distance between two successive parallel lines. Okay. Now the needle is dropped at random. Needle is dropped. So you can think of this as some kind of a floor with patterns. Okay. And you drop a needle on the floor, dropped on the plane at random. Okay. What's the probability? Probability that the needle will meet one of the lines, one of the parallel lines. Okay. So it's a nice type of problem. I want to talk about this type of problem at the very beginning because you see that there probability space doesn't have to be discrete, and you are not told in this type of problem what is your omega, what is your probability. I mean, this collection of events f and so on. So this is you just think of it as some kind of a problem, geometric problem or whatever, and then you need to compute, make sense of this question: what is the probability that the needle will meet one of the parallel lines, and try to come up with some answer. Okay. So, well, I mean, see, so you must think that the plane is sort of, anyway. You have said enough about the problem. So you drop when you drop the needle. Okay, it's going to be like this, or maybe like this, or okay, it looks like these lines. The needle length is too big. Let me draw a picture, different picture here. Okay, sorry, I just not use these lines, but so I'll draw some picture here. It's a little difficult for me to draw the lines. So I'm just going to draw only 2 lines, maybe 3 lines. Okay. And And now you draw a needle. So the needle may be like this, or maybe like this. Okay. Now, so sorry about all the noise. Can't help it. Now, what is the probability it will cut one of the parallel lines? So you need to first make a space, your space omega, okay, or in some way you need to be able to formulate it, okay. How will you do these measurements and so on? What does it mean to say it cuts this line? So you see, first of all, you need some way to parameterize various positions of the needle, correct? So one way to parameterize it is just choose a midpoint and tell me how, where the midpoint is and how it is oriented. Okay. So let us draw a line here like this, and let's draw a midpoint here. So sorry, I must magnify it in order for you to see very clearly. So having explained the problem here, I just do this magnification business right here. This is one of the parallel lines, and now this is magnified. So I'm not showing the other line. It maybe it's far off here. Okay, now plot this midpoint. Now and it's going to be between two parallel lines, right? It cannot. Okay, it may be on a parallel line also. It doesn't really matter. Now you measure the distance of this midpoint from the line that is closest to it. And if it is actually equidistant from these two, choose the line to the, let us say, left of it. Depending on how you draw the thing, maybe it's all horizontal, then you say just choose the one which is uppermost. Okay, so now this is the thing, and so now this is that line, and I look at the distance, and this distance I call it x. And now this orientation of this thing is measured by the angle. So here is, I should just draw the, okay, here is this bit is the noodle, needle, and then here it makes a certain angle. Let's call that angle theta. So, okay, that angle theta it makes to this near the line which is nearest to the needle. Okay, I should draw the needle maybe in a different color. Just 1 second. Okay. So that things are at least clear when you look at your notes later on what is going on. So this is my needle. Now I have extended that line and that meets the parallel line L. So this I should call it capital L, not small l. Okay. Now what are the possible values for x? How large can x be? X can be at most a 0. So 0 less than or equal to x less than or equal to a. Okay. And what about angle theta? Theta can vary between 0 and pi. Okay. 0 less than or equal to theta less than or equal to pi. And if you give me these two parameters, now I say the quantities x and theta determine. I've already told you how to choose the line L. Okay, determine x, determine the configuration, determine the position, the position of the position of the needle uniquely. While uniquely, this should be placed within quotes. Okay. That is having this is unique after having chosen, having dropped the needle. Okay. Now what do you want? You want this needle to cut the line L. Okay. If that happens, how will the how do you express that in terms of angle theta? Okay. So if you if the needle meets your x, so I draw another picture here. Then I draw this. So this is my position, and this is my. Okay, I should have drawn that in some other color. Yeah. So let's just draw this. This is my x, distance to the midpoint. Takes a long time to explain, but it's a very simple concept. Okay, if this happens, then x, so you can estimate the value of x with respect to the angle theta here. Okay, and what we get is that in terms of theta, x is okay less than or equal to, sorry, I wanted blue color, less than or equal to L times sine theta. Okay, so this is a very simple thing, because if it meets, so from here to here will be less than L by 2. Okay, and so you can measure if this angle is theta, so this has to be x times L, L, so some number, so whatever this distance is, that number times sine theta would be equal to x, but that number is less than or equal to L. So I get this. Okay, so you have this is your favorable set. So we want x to be this. Okay, that is, so now what you do is we draw the rectangle. So the space of all possible positions is is actually the rectangle.
So shouldn't it be mod L sine theta?
But theta is always between 0 and pi. Okay, so it's okay.
Oh
Rectangle.
yes, sir.
Yeah. 0 less than or equal to x less than or equal to a, 0 less than or equal to theta less than or equal to pi. Therefore, the favorable set event is equal to set of all x comma theta 0 less than or equal to x less than or equal to L times sine theta. Required probability is equal to, this is some region in the rectangle. So it's reasonable to think that it must be area of this divided by area of the rectangle. Rectangle R. Okay, area of R. And well, area of R you already know. This is A times pi. And area of E. Area of E can be calculated. So this is you just, okay, now I draw just a small calculus problem. You have done this type of thing before so many times, much harder problems. So you draw this 0 to pi and you draw this line, this curve. This is x is equal to L times sine theta. This is theta axis. And now what you need is the area of this shaded portion. So area of E is equal to integral, 0 to pi L sine theta d theta. And that's equal to L times. So small integration problem between the limits 0 and pi. That's equal to 2L. Therefore, required probability is equal to 2L by A pi. Okay. That's it.
Sir, I have a question.
Yes.
Sir, wouldn't theta equal to 0 and theta equal to pi be equivalent?
Yeah, well, I mean, so, okay, so it really doesn't matter. See, the thing is, you fix this point and then this point, you label them A and B. Okay, so now, usually, in this, let me first answer your question in a different way. It really doesn't matter if you just delete one particular value of theta or something because the area doesn't change. But to answer your question in a different way, having marked this A and B like this, if you are going to measure angle from A, theta equals 0 will correspond to point B being above A and the other one being below B, below A. Okay, so those 2 points are therefore distinguished. So yeah.
So how
Okay.
do we
Yeah,
decide
okay.
which is A and which is B? So I didn't
Yeah,
understand.
there you have to make a choice, and now it's really problematic. So how do you choose? You just, you see, this is anyway limiting case. So there is no way to distinguish, maybe in a unique way, but when you vary it in a family, then it is possible to distinguish it. Okay, so that's what I can say. Also, it is possible that the needle is, I mean, like I said, I chose this way, but it could be something like this. Okay. And then you choose this, and should you call it theta or minus theta, and does it matter? But yeah, I mean, we are doing a problem geometry, just call this equal to theta. Okay. It is true that, let us do the following. Since this is a needle, it's going to have an eye, and there's going to be a sharp pointed thing. So the eye of the needle, you can call it A, and B is that thing that is not, that is a sharp point. Okay. Okay, so that will determine everything. Yeah. So that determines the orientation of AB. So it's, you can think of it this way. Yeah. Then also it could be that the thing that it is inclined in a different way, and then B is closer. I suppose There is no, so this type of limiting things, you can just simply ignore it. It is like saying, the contribution for the limiting thing to the area is actually uh, 0. So it just doesn't matter. Ignore. So yeah, we don't bother about that. Okay, that's a because it's a practical problem, and you can ask what is the probability that it falls exactly on a parallel line. So the whole plane is you know um, covered with parallel lines, but the parallel lines themselves occupy only a set of what we say measured zero. So the needle, what is the probability that when you drop a needle, it is aligned on one of the parallel lines? Probability of that is 0. Ignore that and look at the remaining thing. Okay, that's perhaps a better explanation. This brings me to another important concept. This is a very important, crucial distinction. Impossible event and null event. So, what is an impossible event? How would you like to define it? So, is an event that cannot occur. Okay. Null event is an event whose probability equals probability of occurrence. Okay. Is 0. Okay. So these two are two distinct notions. Let me say this. So here is in fact, a very nice, it's a nice question. When you drop a needle on the floor with this parallel line pattern being drawn, now it is possible that the needle is falling along one of the lines. Okay, that's very much possible, absolutely. But the probability of its occurrence is 0. Okay, because we saw that everything is parameterized by points on this rectangle. If it is on this rectangle, what would be my A? My A is 0. Okay, sorry, my X is 0, and my value for theta is either 0 or pi, and they would be just two bits of line segments. No, maybe just a point, perhaps point. They cover no area. Okay, so that's 0. Probability of that occurrence is 0. Here is a situation where a null event can possibly occur. An impossible is an event which cannot occur at all. Okay, so typically this empty set is an impossible event. You can even say that something which is not a member of F is an impossible event, but let's not go into that. So example is this. So, this quite often actually a null event does occur. Suppose I say, pick a real number between 0 and 1 at random. It's most likely that most people will choose a rational number. Okay. But the rational number will measure, a chance that a probability that a number chosen at random in this interval 0 to 1 is rational is actually 0. But nevertheless, This is what I mean by saying that a null event is an event whose probability of occurrence is 0, but it doesn't mean that it cannot occur. This distinction you should remember. Okay, I should move on because there's not much time. I wanted to discuss one other problem before talking about something else. Maybe I do this. Okay. Yeah, another example. So I want to, before launching into more mathematical, more traditional topics, some variety of examples I wanted to discuss. Okay, let's discuss. I had two examples in mind, but I'll discuss only one. This is what is called an encounter problem. So this notion of probability sort of occurs in an ubiquitous fashion. It has so many wide applications precisely because any one particular problem or exercise or whatever is capable of being given any number of interpretations. So it may be just that you think you are just tossing a coin, maybe a bias coin, an event occurring, the head occurring with probability p and so on. But you should think of that as a model, which is very useful in ever so many contexts. So same with the rolling a die and so on. Anyway, what is this encounter problem? So let us say two students agree to meet at CMI cafeteria. Between say 3 p.m. and 4 p.m. They never say exactly what time each person would come, and each person's arrival time is independent of the other. So two students, let us enable them A and B. Okay, and they agree that whoever comes first, each will wait for the other for at most 20 minutes. Well, for 20 minutes, let us say. So you go there, and so maybe A goes there at some time between 3 and 4, and he waits for 20 minutes. And if B doesn't show up, he just leaves. And if B does the same thing, he goes there, waits for 20 minutes. A doesn't turn up, he will just simply leave. Okay. Now, what is the probability? Probability that the two students meet. At the cafeteria. Okay. So what you can do is suppose that solution. So you have to again coordinatize the arrival times. Suppose that A arrives at X minutes past 3. And B arrives at Y minutes past 3. So the two will meet. We don't know who comes first. The two will meet. If while the arrival time between the two is less than or equal to 20 minutes. Okay. So just draw this grid, not grid, rectangle. One is x-axis, other is y-axis. And of course, we know that 0 less than or equal to x less than or equal to 60 and 0 less than or equal to y less than or equal to 60. So you may ask, what if somebody arrives at, just 10 minutes before 4? After 4 o'clock, they disappear because they agree to meet only between 3 and 4. So it doesn't matter. Okay, so the question is meet between 3 and 4. If you like, I can make it very precise. The whole consideration is between 3 and 4. In 3 and 4 p.m. Okay. So you draw. So this is the region that is of interest to us. Okay. So E is equal to set of all x comma y such that x comma y belongs to this. So here is 60. Here is 0 comma 60. If you want to be very precise, 60 comma 0. Okay. So 0 less than or equal to x less than or equal to 60, 0 less than or equal to y less than or equal to 60, and absolute value of x minus y is less than or equal to 20. And required probability, the two will meet precisely, with probability equal to area of E. E is going to be some subset whose area makes eminent sense, divided by area of the rectangle, which is 60 times 60. So this is the line x is equal to y, and then you can draw the line. See, there'll be 3 lines here which are relevant. This middle line is not so relevant. So suppose x minus y is equal to 20. And so that is one of the lines. Which one is that? This is 20 comma 0. So this is a line. Okay. This is a line x, and this is the other line. Y minus x is equal to 20. That is this line, and the region in between the two is this shaded portion. So this is equal to, you can say, 60 by times 60, whatever it is, times 60 times, no, sorry, not times. The whole thing minus, there are two triangles here which are the complement. I am finding the area of the complement minus. So since there are two rectangles and there is a half in the computation of the rectangle, so I compute the complementary set, which is this. So 2 times the area of any one rectangle, that's 40 by 40. Okay, so I compute that 40 times 40. Y 40 by 40, 40 by 40 divided by 2 times 2. Okay. And you can calculate this. 1 minus, so this is 2 by 3, 2 by 3, that's 4 by 9, is equal to 5 by 9. Okay, so that's the probability that the two will meet. I'm just wondering whether I should discuss the other problem which I had. Okay, let me discuss this. It's all right. I think I'm spending maybe too much time, but I want to sort of give you an overview which contains several different type of problems. is just a sort of an introduction to probability. We have not yet started on any specific topics, but just some ideas. What's the other problem I had in mind? Yeah, this is an interesting problem. So you see, everything sort of comes with some kind of a story. So here is the story for this problem. So you decide to go to a concert, yes, okay, music concert or whatever, concert, and a ticket, so the ticket price is rupees 50, let us say. So when you go there, you find that the ticket counter is open, but there are, let us say, suppose that there are 100 people in the queue. People in the queue, and you are the 100th person. And so each person has either a 50 rupee note or a 100 rupee note. Okay, so nobody has any other currency like 20 rupee bill or something like that. Just each person carries either 50 or 100. And then this person in the ticket counter doesn't carry any change. Person in the ticket counter, the ticket seller, carries no change. Of course, if the first person, and so let us say, so it is known that you are the 100th person. It is known that exactly half of them carry 50 rupee note, and the remaining carry 100 rupee note. Okay, so this is a situation, and you see, so suppose the first person goes, he gives a 50 rupee note, he gets his ticket and he's allowed in. The next person gives 50 rupee note, no problem, he gets a ticket. Third person gives 100 rupees, he gets back the change, 50 rupees, he's allowed in. And the fourth person, same, he gives a 100 rupee note and gets the change. And now this person, ticket counter has no change. And the fifth person goes and hands the thing and ticket, that is, he cannot sell the ticket. And it stops. So no ticket is sold from the time that if the person runs out of change. Okay, so this is a situation, rather very peculiar type of ticket counter. Now, yeah, what is the probability? probability. Okay, I said that you everywhere, second person, but I mean, you should say that there are 100 persons. Let us say you are the 101st person. Okay, because you already know what money you carry. So what's the probability? And let's say that you carry 50 rupee notes. So for you, it doesn't really matter. But probability that. So I said something, but I'm not writing it down here. The sales stops if the person runs out of the ticket counter runs out of change. So let me write that before I write it, because that's an important sale of ticket stops if the counter runs out of change. So what's the probability? What's the probability that when it comes to your turn, you get the ticket? When it comes to your turn. With the ticket. You may assume that you have 50 rupee notes. You have a 50. Okay, so this is a sort of a long problem state, but you understood the problem? So it's a very interesting type of problem. So it looks like a very peculiar type of problem, but there are many other questions can be modeled on this. Let me say how to solve this problem. The thing is somehow, so solution, I'll be brief because there's not much time. Okay. So what you do is, so 0, you mark 0 to 100. You mark all integer points on a, I need more space, but let me give myself a little more space. Yeah. I'm not giving myself enough space, but doesn't matter. So what I'm going to do is the following. You can do it for an arbitrary and even, so it's okay. So 100. Now, so if a person presents 50 rupee note, you just go down. So plot the point from wherever you are, 1 unit below. Okay. So it could be that the first person gave change. So his coordinate will be minus 1, 1. And so you see it just dips like that. And then the next person gives 100 rupees. So when you pay 100 rupees, you just move one step upward. And when a person presents 50 rupees, just come down by 1 unit. So I say here, move down or up 1 step, 1 unit, each step, meaning you have to take from 0 to 100. There are 100 steps you have to take each step, depending on So depending on whether 50 rupees is presented or 100 rupees is presented. So this way you will just get a path passing through integer points, and then maybe after a few steps, it just goes here, and then it should end here. This is the line x equal to, this is a line where you are starting with, this is the origin, 0, 0. Why is it that when you come here, the path ends there? That is because exactly 50 people give a 50 rupee note, and exactly remaining 50 people give a 100 rupee note. Okay. So at the end, when it comes to the 100th person, he cannot have any change. You already know that. Okay. Okay. So this is all possible trajectories. So maybe the first person presents 100, then it will go up, and then it goes up again. Maybe another person presents 100, and then it comes down because he got a little change, 50, and so on, 50, and so on. Okay. And then again it moves up, whatever it is. So each configuration, each possible arrangement of the people in the queue, whether they have 50 or 100, is depicted in this exactly one way. Okay. And you know that all these paths begin at the origin and end with the 100. So this could be another possibility. Maybe is finishing up here. Okay. So now, what is it that you do not want? You don't want the sales to stop before your turn comes, right? So that can be stated as follows. The sales stops when the trajectory meets the line y is equal to 1. So y equal to 1 means what? I mean, just the previous time he ran out of all change and somebody presents a 100 rupee note. Okay, so here at the very beginning itself, this person presents 100 rupee note and the sale doesn't take off at all. Okay, so maybe for some other thing, configuration, maybe it is here. Okay, whatever it is. So the moment it touches this line, meets the line, sale stops. So so you want to calculate the probability that the trajectory, the favorable trajectories are those that do not cross y equals 1. And total number of trajectories, irrespective of whether it is favorable or not, total number of trajectories equal to, okay, so you see, you have to start at origin and end at 100. Now 100 comma 0, this also you are ending exactly at the point 100 comma 0 comma 0. Okay, so you must have gone up equal number of times as the number of times you go down, because that's exactly what is told also. Here you see exactly, somewhere I said that known that exactly half of them carry 50 and remaining half carry 100 rupee notes. Okay, so that translates into saying that the total number of trajectories is, well, so you can go up or come down So exactly 50 times you go up and exactly 50 times you go down. But the steps at which you go up, that determines your entire trajectory, because the remaining 50 times you go down. So that 50, you can choose in any of the out of any of the 100. So is equal to 100, choose 50. Okay. Okay, so now we compute the unfavorable trajectories. That's much easier to compute. Those which cross, so the number of trajectories or patterns, trajectories which cross the line y equals 1. So in order to compute this, you see this is a bit complicated. You resort to some trickery. What you do is, so do the following. You so reflect such trajectories about the line y is equal to 1. The first, is a continuation. The first time it touches, the trajectory touches the line y equals 1.
So I don't understand why it's y equals 1 and not y equals 0.
Pardon me? Can you ask the question again, please? Why you take this line? Because this is the first time.
Sir, can you hear me?
Yes? I can't hear you. If you speak a little louder, maybe. Did you ask why the
So I
line y
think my
equals 1?
connection is bad. Can you explain what?
Yeah, so I'll explain.
Yes, so why is
Sorry for the bad. Something like this, let us say. Then suppose this is the line y equals 1. Switch it off. This is a line y equals 1 and about which you flip. I tell you why. So it's difficult to compute all those which are not, see, all those, those which pass through this, which cut this line y equals 1, okay, directly, because they all start with here and end with here, and somehow to implement this. So this trajectory may even make, let me just draw this, sorry, little more. It may meet this line again and then also it can come down, it doesn't matter. Okay, now what you do is I'm just going to reflect this part of the line. So the moment audio recording, please set the recording. What is happening? I'm not. Are you able to hear me?
yes,
No?
sir.
Yes, sir. Yes, sir.
Okay. I got some warning. I don't know what to do about that. Recording could not be started. I don't know what happened. It's okay, forget it. You see, the first time it meets this one, you just go down. I'm going to draw the reflected one in red. And then you just something like this, and then reflect. Oh, not too much. It's a bit difficult to draw this. Yeah. So you see, you just have to reflect about this line. Then somewhere, wherever it meets this, now where will it end? It will end at 100,2 because the point 0 is mapped to 2 under reflection. This end point is mapped to 2. Okay. Now you have got those, and not only that, now you draw any configuration of the kind where you each time you just go one step up or one step down, and ending in 100,2, that will correspond to a trajectory of this kind, where again you perform the same thing. First time it touches this thing, you just flip, and when you flip that, you get back a trajectory which again ends at 0,2, and it touches this. So this is the procedure. Okay, this is a trick. So I'll now continue to write. So the first time it touches this thing, then the resulting reflected trajectory, reflected path ends at 100,2. And any such path, any such admissible path, admissible meaning those which move up or down only one step at a time, admissible path, any admissible path ending at, I'll be very specific, ending at 100,2 arises in this manner. In this manner. This is a crucial point in counting. And now you can see, okay, how many paths are there which start at 0, 0 and end at 100,2. Okay, now this time you must have gone up once more than going down. Okay, so you must have gone up 51 times and gone down 49 times, so that effectively total number of times you have gone up becomes 2. Okay, so the total number of such paths, you have to think about it, the total number of such paths equals, therefore is equals 100 choose 51. Okay, and therefore the required probability is equal to, these are unfavorable ones, so the required probability is 1 minus 100 choose 51 divided by 100 choose 50, and that's equal to 1 minus, so do this simple calculation, 100 factorial, 51 factorial, 49 factorial, here 50 factorial, 50 factorial, a simple calculation, not very much, and that becomes equal to how much? 1 minus this 50 factorial, 51 factorial will leave me with 1 by 51, and this 49 factorial, 50 factorial, that will give me 50. So this is equal to 1 minus 50 by 51, so that is 1 by 51, and that's the correct answer. Okay, you understand? So the crucial point here is you should know, you should first of all be able to model this problem. Here there's not, okay, there may be several ways to model it, but this is one way. And having modeled it, notice that everything starts at 0, 0 and ends at 100,0. So you need a way to calculate those which are favorable to you. And this is a trick. The trick is Those which are not favorable, they cross the line y equals 1. And when you reflect such trajectories, exactly the first time where it touches this, then the resulting trajectory will end at 100,2, and any admissible trajectory, that is those which go up by 1 or go down by 1 at each step, okay, arises in this manner, so long as it starts at origin and ends at 100,2. Of course, so now once you do that, rest of the thing is simple calculation and you get 1 by 51. Okay, maybe just for today I stop here, and let me see how do I get back. Yeah, so I stop sharing. If you have any question, we can discuss that. If you have any questions, if you have any doubts, you can ask me. I know I still have about 10 minutes, but the next topic I want to talk about is conditional probability. I can do that now, but perhaps it's better if I start on it in the next lecture. Any questions? Well, I see something in the chat box. For every orientation of theta. No, we don't assign probability for any one particular choice of theta or whatever. Okay. So first of all, when we describe that space 0 less than or equal to x less than or equal to a, and then I think maybe I use theta 0 less than or equal to theta less than or equal to pi, that sort of parameterizes the positions, and you don't assign probability for individual points. Okay, so this is how the discrete probability varies. I mean, usually in your 12th standard and so on, your probability space, that omega will be a finite thing. Okay, and for each point in omega, that's an elementary event to which you will associate probability. Here we are moving to a drastically different type of situation where your space omega is not necessarily finite. As I mentioned in the very first lecture, it could be infinite. It could be not just infinite, it could be a continuum of points. It can be points on the real line, it can be a region on a plane, it can be much more complicated than that. So each time, what is the probability? I should say, first of all, I should say what is this F. In all these things, strictly speaking, I should say what is the collection F. Okay, so the collection F will be subsets of the plane for which it is meaningful to talk about area. Okay, and collection of and then what is the probability? The probability is area of your event. So an event is just a subset of the region which parameterize the position of needles. So that region, so I was about to say, what is the probability you assign to an event? An event is a region to which you can assign notion of area. So probability of the event is area of the event E divided by area of the whole space. Okay, the area of the whole space was just a rectangle for whose area was just a pi. And for our problem, we described the favorable region, and therefore we did that. The important thing is you just cannot talk about probability of a specific position in which the needle is falling. If you do that, it will be probability of, it will be area of a point divided by area of the thing, but area of a point is 0 and therefore it is 0. Okay. Yeah, so that answers that question. And then we travel on a grid in XY plane to find the probability that we will stay below y equals x. So it depends on how you model it. I modeled it by saying that while you go up or down, I said down when the person presents a 50 rupee note. Okay. There are, like I said, many ways to allocate points on the grid and then so on. But the way I said it, that's why it's go ups or down. And then therefore the analysis that I did is valid. But perhaps it's not the only way to model it. You could have a different algorithm, but whichever algorithm you do, finally the calculation should be essentially the same. Any question? My home is very close to the mosque, so you can hear this azan. There are no questions. We will stop here for today. Okay? I'll end the lecture.
Thank you.
Thank you, sir.
Thank you, sir.
Welcome.
Thank you,
And
sir.
we'll meet on
Thank you, sir.
Monday. There will be some tutorial either Friday or Saturday. Further announcement will be made.